Okay. So yesterday we have started with unit number 6, that is VLSI testing and analysis. And before we ended, we had discussed about how to detect stuck at 0 and stuck at 1 faults by taking examples of 3 input AND gate and 3 input OR gate. So we take our discussion ahead today. Now testing sequential logic and test pattern generation. So these two are actually connected to each other. So we'll try to understand why we need to have what is called as test patterns or test vectors. So yesterday we had taken example of a single gate, 3 input AND gate and 3 input OR gate. On the other hand, if we have an AND OR logic as below, okay, so you can say consider the AND OR network shown below. So if we consider this AND OR network, we can understand that even to find out the input combinations to check for stuck at 0 or stuck at 1 faults in a simple 3 input AND or OR systems, it takes so much of thinking. So imagine that how much complex it would be even to find out what are the input combinations required to check stuck at 0 or stuck at faults at any point of the system. So we can have both kinds of faults at any of the 9 inputs. So any of the 9 inputs here from A to I can suffer either from stuck at 0 or stuck at 1. At the same time, it is also possible that the outputs of the AND gates can also suffer from stuck at 1 and stuck at 0. At the same time, it is also possible that the final output Y, that is output of OR gate, can also suffer from stuck at 0, stuck at 1. So we say that these are the points at which there can be stuck at 0 and or stuck at 1 faults. ठीक है ना? So that is why depending upon the given network, we have to find out what is called as test vectors. Test vectors. So we can say that the input combinations for the individual gates A, B, C, D, E, F G, H, I are known as test vectors or test patterns. Okay. So now this is an example of a combination system. So we can also have sequential system because we know that it is digital system can consist of combinational networks or sequential networks. So we can say just like we must have test patterns for testing combination logic, we need similar testing procedures for sequential logic. Okay, now we have some statistics which actually tell us what is the complexity of the um, test sequences. So by analyzing small systems with small number of states and extending our analysis to larger systems, we can take an example. Okay, so we can say consider a sequential network having number of inputs equal to 5, number of outputs equal to 1, and output states equal to 4. Okay, so consider a sequential network having 5 inputs, 1 output, and the number of output states is equal to 4. So if we use a brute force approach for testing the above network, we must apply 2n minus 1 number of input sequences. So understand, number of output states is denoted by n. Okay, so we must apply the number of input sequences, that is equal to 2 into 4 minus 1 equal to 7. So it is very natural that because the number of inputs equal to 5, so we can have 2 raised to 5, that is 32 combinations. So at time t equal to 1, we can apply 2 raised to 5 input combinations. Similarly, for 2 to 7. Okay. Thus, total number of test sequences is 1, 2, 3, 4, 5, 6, 7 is equal to this will be 2 raised to 12, right? It will not be 2 raised to 35, right? Or it will be 2 raised to 35. Yes?
35 only, sir.
Yeah. So we see for such a small system also the total number of test sequences goes to 2 raised to 35. That is in millions, right? So this is not feasible because practically digital systems are having many number of inputs and large number of output states also, so which is not feasible. So what we do is that um, to derive a relatively small set of test sequences, we convert the sequential network into an iterative network. And use one of the standard methods for testing combinational networks. Okay. So this actually takes us to what is called as B.I.S.T. Okay. So we discussed about how to test sequential logic, so test pattern generations. Now we come to B.I.S.T. So although I told that I have shared one PDF on your Teams, BE8 Teams theory folder about B.I.S.T, but still I thought that we will speak something about that today again. So B.I.S.T. So B.I.S.T is an abbreviation for built-in self-test. So built-in self-test, the definition of built-in self-test lies in the word itself. So it's very simple. So the concept of adding test logic to an IC is called as BIST. Okay, built-in self-test. The concept of adding test logic to an integrated circuit is called as BIST. And BIST is a set of structured test techniques, is a set of structured test techniques used for testing both combinational and sequential systems, such as memories, multipliers, and other embedded logic. Okay, so what the basic principle of BIST is this, that the basic principle is to generate test vectors basic principle is to generate test vectors on chip. Is very important. On chip. Okay, basic principle is to generate test vectors on chip and apply them to the DUT. DUT stands for device under test. So whichever device or whichever system is to be tested for faults, the test vectors are applied to them. Device under test. Okay. on chip and apply them to the device under test. And observe response. So the generic B.I.S.T scheme can be shown as follows. Generic B.I.S.T scheme. So I'll insert a photo here. You'll come to know what I'm speaking about. This is a very simple. So we can say that this entire thing is actually a on chip. On chip means along with the logic, along with the microprocessor, along with the microcontroller. So we see here that we have an on chip test generator. Okay. So we have this on chip test generator, and these are the normal inputs from real world. So now we see that we are having a multiplexer here, and this is the DUT, okay, device under test, on which we have to perform fault testing. So the normal inputs coming from real world are not directly applied to the DUT, which is in normal case. So in a normal integrated circuit, which is not having an inbuilt test facility, in that case, what we will do is we have to directly apply these inputs here. That is the case with integrated circuit with no inbuilt testing facility. But here what is happening is we want to include the testing facility here. So we are having a 2:1 multiplexer here. We can say this is 0 and this is 1. So this is our select line, which can be 0 or 1. So if I want to test the device for presence of faults, what I do is that I apply logic 1 to the select line. So the test vectors which are generated from here, they get applied to the DUT, and the DUT's response is actually recorded by a response monitor, and then the error signal is generated. Okay. On the other hand, if I keep the select line as 0, then the test vectors will not be applied to the inputs, but rather normal inputs will apply. That is why such chips which are having a B.I.S.T facility embedded inside, they operate in two modes. One is the normal mode and one is the test mode. So we can say that the above is a block diagram. So the above is a block diagram of an IC with B.I.S.T, B-I-S-T. So we can say when select equal to 1, the IC is in test mode, and when select line is equal to 0, IC is in normal or the working mode. Okay, it's very simple. So it's a basic B.I.S.T scheme. Okay, so a classic example of where B.I.S.T is used. B.I.S.T is usually used for testing memories. We will give an example now. So using B.I.S.T to test memories. So memories can be either RAM or ROM. Again, I'll insert some pictures here, so we'll come to know. Something got lost actually. Anyways. Okay, so this is a B.I.S.T controller. So we have a dedicated section called B.I.S.T controller, and you know that because it is RAM, so it is having ability of read and write both. Okay, so it's like this. So we have a write data generator here, which will generate the words. Okay, so this output of the write data generator is given to the data in of the RAM, and we have an address counter here which is responsible for incrementing the address. So address is incremented, new data is written, again the address is incremented, and the new data is written in the new location. And we also have the read data generator here. Okay, so we have the address input, data in input, and we have data out. So this is similar to the system. So we can say this RAM is the DUT here. So we can say this RAM is the device under test, and the write data generator is responsible for generating test vectors. Okay, and then the output data out is actually response. So these are the responses which are recorded, and we have a standard data set here. So we can check that whatever is at the data output, was it equal to or same as what data was written inside. So we have a B.I.S.T controller, we have a DUT, and we have comparison of responses, right? So now a modification of this thing is that we combine the read data generator and compare with what is called as an MISR. MISR basically stands for multiple input signature register. So many a times the output data seems are too long in the number of bits. So what we do is that the test circuit is simplified by using a signature register. Okay, so the test circuit is simplified by using signature register, which compresses the output data which compresses the output data into a short string of bits, into a short string of bits called signature. Okay, so we have what is called as MISR. So MISR, that is multiple input signature register, combines and compresses combines and compresses several output streams, several output data streams into a single signature. Okay. Okay. So we have a modification of this above block diagram as follows. Everything else remains the same. Only difference is that two blocks have been removed. So the address counter and the comparator have been replaced by MISR. Okay. So everything else remains the same. So this is a combination of read data generator and the compare block. So combination of read data generator and compare. Otherwise everything else remains the same. Okay. Another important block in this is called as LFSR, that is a linear feedback shift resistor. Okay. Is often used to generate test patterns, right? So we will just paste one more figure, which is an example of LFSR, that is linear feedback shift resistor. And when you see that, you will come to know that you have seen this circuit before. Okay. So it is this thing, right? Can anybody tell me what is another name for this? You must have seen this in second year. Yes. What
PN
is this?
generation.
Pardon?
PN sequence generator.
Sequence, PN sequence. Another name for PN sequence. It is called as PRBS or PRPS, that is pseudo random bit sequence generator or pseudo random pattern generator. Okay. So this is very, very standard. Okay. So I think so. In your second syllabus, you have this PRBS. So it is called as a PRBS because it is a random, it is a sequence generator, but the sequence which is generated is random, and it is not pure random, it is pseudo random. Why it is pseudo random? Because within a set of unique states, the sequence is random, but that set repeats itself. That is what is called as a pseudo random bit sequence. So it's very, very simple. Another name for this is actually PRBS. So the above circuit is also known as PRBS or PRPS. That is pseudo random bit sequence or pseudo random pattern generator, PRPG. Okay, it's very simple now. For example, if I have the output initially as 0 0 0 0, then this particular system cannot produce any other count, because here also it is 0 here 0, so always 0 will get rotated. So I need to have facility inside my system to introduce a 1. So for example, I assume that if I set the output to 1 0 0 and 0, so 0 comes here, 1 comes here, so then will come here, right? So that is why whenever the rising edge strikes here, basically it is a synchronously clocked system, so it is generated here. So what happens is that this goes here, this goes here, this goes here, and this goes here, right? So if we start with 1 0 0 0, so we have Q3, Q2, Q1 and Q0. If we have 1 0 0 and 0, so the next sequence will be 1 0 0 and 0 and 1, example 1. The next will be 1 1 0, and again we have this thing. Then next we have 1 1 1, and we have 1 here. Then we have 1 1 1, 0 here, 0 1 1 1 1 0 1 0. Then we have again 0 1 0, 1 and 0 1, and we have 1 0 1. Again we have here, and then we have 1 1 0, 1 and 1 0. So 0 1 1 0, has it repeated here? No, it's not repeated here. Let us see. So we have 0 1 1 0. 0 0 1 1 has come somewhere. 0 0 1 1 has not come. Okay, so then we have 0 0 1 here, then we have 1 0 0 0, then we have 0 1 0 0. Okay, yeah, 0 0 1 0 not come. Let us see. So then we have 0 0 1 0. Okay, right, 0 0 1 and 0. Then we have 0 0 0 1. 8. Yeah, it has returned now. Yes. So if we see, if we consider this is MSB and this is LSB, this is MSB and this is LSB, then the count would be 8 12 14 15 7 11 5 10 13 6 3 9 4 2 1 and 8, right? So total number of states are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15. So 4-bit PRBS is going through 15 unique states, right? So this is totally 15 unique states, and this repeats itself. After 8 we will again have 12. After this we will have 12 here. Okay, so 1 0 0 1, right? So this is called as a PRBS. And PRBS or PN sequence generators are used in the B.I.S.T technique since they can generate a large number of test vectors or patterns with a small amount of logic circuitry, with only a okay. Okay. Yes. We already discussed yesterday that JTAG, that is joint test action group, activity group, or access group. There are many long forms of JTAG. Some people say it is joint test action group. Some say it is joint test activity group. One place I read that it is called as joint test access group. Joint test access group. Whatever you call as, it is IEEE standard 1149.1. That is more important. Okay. So if you see that the JTAG which is used to test internal circuitry looks something like this. So these signals are very important. Test data input and test data output. So many times it comes in exam that which are the standard signals associated with the JTAG protocol. Okay, so there are 5 basically. They are called as JTAG signals. So if somebody was watchful in carefully seeing the JTAG download cables from microcontrollers, so you will come to know that it is same as this thing. Okay, so you see that JTAG pins or JTAG signals it is called. So first is TDI, second is TDO, third is TMS, fourth is TCK, and fifth is TRST. Okay, test data input. Very simple to remember. Test mode select. TCK, T for test, CK for clock. Test reset. Okay. TDI, TDO, test mode select, test clock, and test reset. Okay. So this is an optional signal. You may or may not find it. And for external testing, so here these are called as boundary scan cells. Okay, and it's cascading basically. So the TDO of the first system is connected as an input to the second system. So it's cascading basically. So it all goes like this. Okay.